Well, good on you all for giving up a bit of time at the weekend. Hopefully this will help you prepare for your Level 1 Mechanics exam. And as you'll have seen, we're running some genetics and acids and bases at later in the week. And so if you haven't already, you're welcome to register for those. And I'll send out emails with the URL closer to the time for those ones. Thank you very much to those of you who have given feedback in terms of what you'd like to cover. I've prepared a few things that we'll go over. These are, common approaches to exam questions and some of the concepts that often prove difficult for students. So we'll go through those, and as we do, if you've got any questions, please feel free to unmute yourself and ask. You can also put questions and things in chat, but I might not, as I'm going through a question, I might not be able to see what's going on in the chat, so it might be easier if you just unmute and ask the question. My name's Douglas Walker. I'm a teacher at St Patrick's College in Wellington, and I've taught Level 1 Science for a number of years. I originated in Scotland and taught for a couple of years in England before coming over to New Zealand. We work on all the externals. I know that for some of you, you do maybe one external in science and externals from the physics, chemistry or bio standards. But today we'll focus on Level 1 Mechanics. Okay, so you should be able to see my screen, and I've just more than anything else, just to help guide my thinking, I've put down some of the issues that you guys have addressed or asked to be addressed. And I'll share the link to this. So I'll put some notes into this and I'll share the link to this slideshow at the end. So we've asked for some advice for common approaches to answering questions. So I'll take you through what I call the guess method. Hopefully some of you have seen it already, but it's a really standard approach to calculation questions, and it should give you the confidence to make a start on a question. And once you've made a start, if you can follow the process through, you should be able to get at least some credit. Even if you make a mistake, you're normally able to pick up some credit for an incomplete answer. Along with that, I'll go through some ideas for how to answer explanation style questions. So that's often your merit or your excellence. Somebody had asked for the link between work and power, so I'll talk through that. And we'll have a look at a few free body diagrams. This one's a classic, the justifying the difference between energy values, so at the top of a slope and at the bottom. So we'll have a little look at a simulation to help us understand what's going on there. And I'll take you through a shortcut that links both of the energy equations. And hopefully that'll help you with any of those questions in the exam. It's quite a common question around energy, so I would expect to see it in some form in your exam this year. And we had a question about explanations relating to pressure, so we'll go through that as well. If you registered a little bit later, then I probably haven't had time to go through the spreadsheet and pull out the things that you guys wanted to work on, but as we go through, feel free to ask me to go over anything that I may need to give more detail on, if there's something you're not sure about, and if we've got time at the end, if there's other things that you'd like help with, just flag those up and I can go through those as well. Any questions before we begin? Okay. So in the exam, you will get this information here. So these are the formulas that you're given. You need to be able to rearrange those to deal with situations. For example, if you needed to know the area, that's this capital A here, then you would need to be able to rearrange this equation. And if you want a little bit of help with that, if you're not sure how to do that, then make sure you hang around at the end and ask me, and I'll go through that. We've got G, which is 10 newtons per kilogram or 10 meters per second squared for acceleration. And that's an important number to know. So if we've got a calculation question, then we're going to use what I call the guess method. So with that, we use the acronym GUESS, and each letter represents a word. G stands for given, and that is what values have you been given in the question. And you write those down with the symbol next to them. So I think what I'll do is I'll pop in a little example once I've gone through the method and show you how that applies. The U stands for unknown. So what value do you need to find? And that should be quite obvious from the question. So again, we'll write that down with the letter representing what it is that we're trying to find. For example, if you're looking for power, then you're probably going to write a capital P equals question mark for that one, for your unknown. By that stage, we'll have a number of quantities written down, both what we've been given and what we've been asked to find. And then we will hopefully be able to find an equation that links those. So E is for equation. So you can refer to that resource booklet if you need to and identify an equation to use. And the first S stands for substitute. And so that's dropping the numbers in to replace the letters in the equation. And then the final S is solve. And so that's where we write our final answer. So calculate, write our final answer. Whoops. And you always want to check the units with that one. And you probably want to do a common sense check as well. So you want to make sure that the value that you've given is appropriate, so it makes sense. I'm just going to pop back over to the waiting room just to make sure I haven't missed anyone. I think we've got everyone. Okay, so let's see what that looks like. I'll pop in a new slide here. And I'll see if I can grab a question from one of the papers. Okay, so if this was our question, then we're going to use this example just to work through the guess method once. So what values have we been given? Well, we've been given mass is equal to 9.90 kilograms. Looks like we haven't got any other information there. And because this is the first part of the question, if we look back up and make sure there's no other information on previous questions that's relevant, then we might be a little bit stuck here. But let's go on and write down the unknown. So what is it we're trying to find? Well, we've been asked to give a calculation for weight. Now, weight is a force, so I tend to write it as F equals question mark. And I'd sometimes use FW as a little subscript, just to indicate that it's weight force and not a force acting in a different direction. Okay, so at the moment we've got weight force and we've got mass, and we might be a bit puzzled as to how we're supposed to work that out. But if we drop back to our resource booklet, we should remember that we know the value of gravitational field strength, G, or acceleration due to gravity. And so one of the other values that we have been given is G is equal to 10 newtons per kilogram. I'll just write it like that, if that's okay. So then the next letter in the guess method is the equation. So what equation do we have that links those? Well, if we flick back over here, then we've got force over here. We've got mass, 9.90 kilograms, and we've got acceleration. We remember that G can be called acceleration due to gravity, and you may have seen that formula written as F equals mg. So that's the formula we're going to use this time. It has both of the things that both of the values we've been given, and the one thing that's our unknown. So we drop back over here and we write in the equation. F equals m. I'm going to call it mg because I've used the letter G up here. And then S is substitute, and so F equals mass, 9.90 times G, which is 10, equals, and then solve. F equals, so 9.90 times 10 is 99 newtons, the units for force. And I'm just going to check that that makes sense. So 99 newtons, 9.9 is about 10 kilograms. We're timesing that by 10, so we'd expect the answer to be pretty close to 100. 100 newtons of weight is probably about 1/6 to 1/8 of an average human's weight, and so that does seem to make sense. So I'm happy with the answer. Any questions at this stage? Feel free to unmute your mic if you'd like to ask a verbal question. I'm just going to drop out and check the chat. Yep, nothing in there. Okay, so that's the guess method. Now, the majority of the time, students who struggle with calculation questions in mechanics or physics often don't know how to make a start to the question. So using that, yep, go for it, Eden. Okay, yeah, really good question, Eden. Thank you. So Eden's asked, why is it showing as newtons and not kilograms for weight? And that's a really good point, because the question asks, what is the difference between mass and weight? Mass is the amount of matter that makes something up. And so my coffee cup has a certain amount of matter, a certain number of atoms, if you like, that make it up. And that is what represents the mass. So the mass is the amount of matter, and that's measured in kilograms. The weight is a force that comes about because the mass of the cup is inside a gravitational field, and that produces force downwards, which we call the weight force. Okay, so because weight is a force is measured in newtons. Mass is the amount of matter in an object. And that is measured in kilograms. That's why the force is measured in newtons. Is that all right, Aidan? Awesome. Okay, good question. So the guess method should help you make a start on a question. If you can make a start, you should be able to get the G and the U, the givens and the unknowns. And then it's a case of finding an equation. And the majority of the time, you should be able to find one equation. Occasionally, you will need to you'll need to use two equations, one equation to get a value that you can then feed into a second equation. And so you probably want to give that a bit of practice in the run-up to your exam. And then if you've got your equation, it's substitute and solve. So you should be able to make a start, and you should be able to get to an answer. Often the mark scheme gives you credit for various stages of the answer as well. So even if you don't get all the way to the correct final answer, you'll get some credit there. Okay, so moving on to explain style questions, and this is really, you need to be nailing these to get your merits and your excellences. For the explain questions, Henry, can you just keep your video muted? Thank you. The explain questions, you always want to try and find an equation to support your answer. So I'll just see if I can find an example and post it in there. So sticking with the Wakayama question from the 2017 paper, which just happens to be the one that I've got open up. So we've got a situation where the Wakayama sinks further into the water when a 67 kilogram paddler sits in it. And just for a bit of context, this is a type of canoe or boat that would be in the water. And the previous question gave us the dimensions of the hull of the boat. So we've got a mass sitting in it. So the idea is that the boat sinks further into the water when somebody sits in the boat. That probably makes sense based on our experiences. Okay, so we've got to explain why it sinks further into the water. And so what we're looking at here is some values that we've got. Well, we've got mass, that's little m, nope. And we've got, if we've got mass, we've got weight force as well. From a previous question, we've got the area of the hull, so I'll use capital A for area. And given those quantities, we should know the equation P equals F divided by A, so that's pressure equals force divided by area. And we're going to use this equation to help us give a full and complete answer. So I would write down the equation just as a note. You could even write it on the side of the page. And then we might say that when a person sits in the armor, the mass of the boat and occupant has increased since the equation that we used before, weight force is equal to mass times gravitational field strength. A larger mass will lead to a larger weight force. And then since P equals force divided by area, pressure equals force divided by area. So again, writing it down just to remind myself to talk through each of the values. And area remains unchanged. An increase in weight force will lead to an increase in pressure. So as the number on the top increases, so the numerator gets bigger, if the denominator stays the same, then the pressure is going to increase. So the value over this side will increase. So that gives us an increase in pressure. This causes the Wakayama to sink further into the water. Until greater buoyancy force, so that's the upwards acting force on the boat from the water, balances the forces, balances the weight force, I can say that. Okay, any questions around that one?
Hello.
See somebody's unmuted their mic. Did you want to ask a question?
Hi, yes, I wanted to ask a question about the forces. Do we need to explain and include the forces into the
You're welcome to
explanation
type it
questions?
into chat if your mic's not working. Okay, if I see it pop up, then I'll flick back and answer that question. So just a reminder there then, use the equations to support your answer. And if you write the equations you're going to use, then make sure you tick off each of the terms. Often the difference between merit and excellence for that sort of question will be, stating that something remains the same. So in this case, area remained constant or unchanged. And unless you specifically stated that, you wouldn't get perhaps the full credit for the answer. Okay. So another point to cover then, I think we're moving on to perhaps more actual content now. There was some questions around free body diagrams and how we draw those and then what sense we can make of them. And again, this is quite a common question in the exams. So hopefully I can draw some arrows on here. And I would always draw my arrows coming from the center of the object. We've got a drone, just because I pinched that image from a worksheet that I use with my students. When a drone's at rest on the ground, we should know that at rest means that the forces would be balanced on the drone. So I'm going to draw an arrow coming down from the center of the drone, and I'll make that a little bit thicker, so hopefully you can see it a bit more clearly. And I'll make it a different color so you can see it over the drone in the background. So this red arrow here would be our weight force. And if it's at rest on the ground, then we know there must be an equal size force acting upwards. And so that would be the support force. There's a few different terms you can use for the support force. You might call it reaction force or normal force. I tend to find support's most commonly used, so I'll use that today. And I'm going to draw a support force. It should be the same magnitude. By that I mean the same length as the weight arrow, and you've got to be quite careful about that in your exam. Make sure that you draw it, if you've got a ruler, then actually measure the arrows and make sure that they are definitely the same length. So I'll just move my support arrow down here, make sure that it's about the same size as the weight. There we go. And I'll call that support. If you don't bring a ruler into the exam with you, folded bit of paper, edge of a calculator, just be very careful that the arrows are of the same magnitude. You could even just write a statement to the side to say, support equals weight, if you want the forces to clearly be the same size. We might want to, sorry, I'm just pausing because I've got a question come through. Do we need to include the forces acting on the object into the explanation? I think it's good practice too. It's possible that there would be some credit related to that. Often the question will have little bullet points that'll ask you to cover a number of things, like name the forces in this example. So yeah, I think it's a good idea too. You don't always need to, but I would. And Nate, so you couldn't use a double-headed arrow to represent this. I'm not sure. Oh, a double-headed arrow? I wouldn't use a double-headed arrow. I would make it quite clear that they were two different arrows. I would label them with words. And as you can see in this case, I've tried to use different colors to show you that. There is a little trick you can do. It's a more mathematical trick where you can actually put like an equal sign across the lines to indicate that both of the lines have the same magnitude. But that's a little bit hard for me to show without doing it by hand. So to do that, I would put a sort of equal sign across the support arrow and an equal sign across the weight arrow, just to show that it's just a way of annotating them to show they're the same magnitude. Another question, so mass isn't the same as weight, but mass is the same as weight force? No, I'm sorry if there's something I've said that's maybe led you to believe that. Mass is a different thing to weight, but weight comes about, the weight force comes about because mass is inside a gravitational field. So Earth's got a gravitational field, and anything with mass inside that gravitational field has a weight force which acts towards the center of the Earth generally. Yeah, does that help, Nate? Do you want to ask for any clarification on that? Again, weight is always measured in newtons. It's a force. And I'm trying to say weight force as I'm talking through it, just to be clear that, you know, there is a force. It would be you'd be absolutely fine not to use the term weight force. You could just use weight, and that means that, you know, that's understood that that is a force. Okay, so moving on to the next diagram. Thanks for those questions, guys. We've got the drone rising at a steady 5 meters per second. Now, the weight of the drone will not have changed unless we, you know, took part of the drone out or added something to it. And so the weight force should be exactly the same. Now, if it's rising at a steady 5 meters per second, that means it's a constant speed. And this is the part that really trips up people. Whether the object is at rest or at a constant speed, the forces are balanced. And so we should have an upwards acting force that's the same magnitude as weight. We could possibly go a little bit deeper with that. I'm going to keep it reasonably simple, although I might talk over a slightly harder concept in a moment. This time, however, it's not called the support force because you only get a support force when the object is on top of another solid object. So like a car on a road, for example, would have a support force. You're probably sitting in a chair, so that's providing you with a support force. But because it's in the air, there is no support force. So we need to change the name of the force. And in this case, we could probably call it lift. Okay. Now, if we look at that in a little bit more detail, and this is probably going beyond what you really need, if the object is rising, then it's bumping into air particles as it's moving upwards at a constant speed through the air. And so in actual fact, what we would have is an additional arrow, and I'll make this one sort of pinky color. Oh, that's maybe not too easy to, that might be a bit hard to tell apart. Let's go green. And I'm going to make that quite small, hopefully still vertical. Okay, and the green arrow represents air resistance or friction. I like the term friction because it applies to every situation. Whether it's a boat going through water that is bumping into air particles and water particles, you could talk about air resistance and water resistance and use terms like drag, but friction covers everything. And so friction's a really good term to use in your answers. So the green arrow is friction and the red arrow is weight. And because the total downwards force must be the same as the total upwards force, I need to make my red arrow, well, I can't make my red arrow a little bit smaller because that would actually change the weight of the object. What I need to do to make sure the forces are balanced is make the lift arrow slightly bigger to account for the extra length of the green arrow. So just to help you out here, I might add this green arrow onto the red arrow, and we can see the total downwards force from those two arrows, and then the lift force must be the same as both of those. Now that's going into a bit more detail than you often need in your answers. I'll just check that my arrow is the same magnitude, a little bit longer. Okay, there we go. Not quite vertical, but I hope you'll forgive me. All right, so the total upwards force equals the total downwards force because the object is at a constant speed. Any questions about that? Okay, so then moving on to accelerating. Oh, yeah. Somebody's just raised their hand. Do you want to ask verbally or do you want to type it in? I saw somebody raise their hand, but I haven't seen a question come through. What's the support force in space? Okay, cool question. You normally, if you were dealing with space as sort of, if you were thinking there was no gravitational field in space, i.e. you were far enough away from Earth or the Sun or any other object of mass to ignore weight, you probably wouldn't have a support force. You possibly could have a support force if you had like little magnetic boots on and you were walking on the outside of a spacecraft, in which case you might have a magnetic force going towards the craft and a support force acting against that. But in most situations you wouldn't have a support force in space because you wouldn't have a weight force if you're talking about space as being far enough away from any gravitational field to ignore it. Yep, force is weight, or better yet, weight is an example of a force. So examples of forces are, weight, support, friction, lift, buoyancy. You can probably get away with using terms like thrust for a kind of generic forwards acting force on free body diagrams. Okay, and I'll just pop back over to the presentation. Keep those questions coming through if you've got them. Okay, so if the drone was accelerating upwards, again, the weight force can't have changed. So I'll pop a weight force over here. And there's going to be some frictional force. The frictional force could get a little bit complicated here, so I'm going to simplify it a little bit. And I'm going to ignore the frictional force in this situation. And I'm going to use lift because if the object, we should probably throw a little bit of friction in. I won't go into detail about why that might be a problem because it's a slightly higher level concept. But if we've got frictional force in here, let's just assume that it is it started from stationary on the ground and it's accelerating upwards. Then we're going to have some frictional force as well. And the lift force, in order for it to be accelerating, there must be a net or unbalanced force upwards, according to Newton's second law. And so we're going to make the lift force quite a bit bigger. And it's a good idea for your diagrams, if the object is accelerating, make the force in the direction it's accelerating clearly bigger. So that there's no doubt in the marker's mind as to whether you understand the concept or not. So there's our lift. Lift is much bigger than the combined weight and friction, and so the net force is upwards, and the object is accelerating upwards. Any questions around that? Okay. moving on then, we've had some requests to cover work and power. Work, which is also known, can also be called work done, is energy. So you can call it work or you can call it energy. It's the same thing. And so it's measured in joules. And we normally deal with energy in terms of energy transferred, so energy being transferred from one form to another. So if you push a table across the floor, then you're using some of your chemical energy in your muscles to give yourself some kinetic energy, and you're also transferring kinetic energy into the table in order to give it some velocity across the floor in terms of getting it to move. So I just saw a question, apologies I didn't see it a moment ago. How does friction affect the speed? So I think that's coming back up to here. And I'm going to assume that you were asking about the rising at a steady 5 meters per second. If I'm wrong, then please correct me. The object traveling at a constant speed, it's going to be bumping into a certain number of air particles every second. And that is what gives the frictional force acting against it, or against its direction of motion, if you like. That means that as long as it's going at the same speed, it's always bumping the same number of air particles out of the way every second. And so the force acting against the object is consistent. And so the friction would be at a certain size. And in terms of how does it affect the speed, in this situation it doesn't affect the speed because the object is already at a steady speed. So the forces are already balanced. If we considered that with an object that was falling, so let's say we flew the drone into the air and then we cut the motors and it accelerated downwards, then the friction would, as the drone gained a downwards speed by accelerating due to gravity, then it would be bumping into more and more air particles every second, and so the frictional force would get bigger and bigger. And the frictional force would reduce the acceleration of the object that was falling. And so its rate of acceleration would decrease. But while the rate of acceleration would decrease, the speed can still be increasing. So just take a moment to process that. The object's accelerating downwards, it's falling downwards, getting faster downwards. The faster it gets, the more air particles it bumps into every second, so the bigger and bigger and bigger the frictional force. And that means that the net force gets smaller and smaller and smaller, and so the acceleration gets smaller and smaller and smaller. At some point, that frictional force, the object will be going so fast that the frictional force will equal the weight force. And at that stage, the object stops accelerating, and we say that it has reached what we call terminal velocity, the fastest speed that it can go at in falling. If we were then to make the frictional force bigger by, say, popping a parachute, then suddenly the frictional force would be a lot bigger. And that means that there will be a net force upwards, which would cause the drone to decelerate or to accelerate in the upwards direction. Bear in mind, it can still have a downwards speed, but be accelerating upwards, i.e. that's when it's slowing down, okay, because we've just popped a big parachute out the top of it and increased the friction. And then its because it's accelerating upwards, that means its speed downwards gets smaller and smaller and smaller. And as its speed downwards gets smaller, the frictional force, the number of air particles it's bumping into every second, that's the drone and the parachute now, gets smaller. So the frictional force gets smaller until at some stage, the frictional force will then equal the weight force, and the object will be traveling at a constant speed again. But now that constant speed will be lower than it was before. So it's quite a lot to take in there. Do you want to take a moment to just think about that and ask me any questions on it? So I've got a raised hand from Clara. Do you want to go ahead with a verbal question, Clara? Oh, sorry, I think I see one in chat there. So just give me a moment, guys. I'm going to go over the questions that I've got in chat. So Rachel's asked, would we be marked down if we didn't include the friction force and just wrote weight instead? In this situation, in most cases, you'd probably be all right with just the weight. I probably would include friction. It might have been better for me to use a horizontal example like a car, because then the weight is acting downwards, and if it has a forwards acting force, then it's going to have a frictional force in the opposite direction as well. So I probably would include the friction, yeah, in most cases. It depends on the situation as to how desperately you do need it, but I would try to include every force that was acting on an object. In terms of understanding how to know which type of force each situation would be, that is a great question. Friction is whenever an object is rubbing against or bumping into particles. So if a submarine was moving through the water, it's bumping through water particles, and so we would call that friction because the water particles are rubbing against the surface of the submarine. If a car is driving along the road, then it's bumping into air particles. That's a type of friction, and it's also got friction between the tires and the road. If the lift is generally only the case for objects that are shaped like wings, and so you could use lift in that situation. If it was a hot air balloon, it would probably be buoyancy. And so I think a lot of that just comes through practice, so looking at different situations and working out or making sure you've got the right names for those situations. But if you want me to go over that in more detail, I'm happy to cover that at the end. I've got a question about what's terminal velocity. Terminal velocity is the fastest speed that something can reach when it's falling through the atmosphere. So if we drop a pea off the sky tower, so a little green pea, it doesn't have a very big mass, therefore it doesn't have a very big weight force, and so it's going to reach a stage quite quickly where the air particles that it's bumping into enough of those every second to equal the weight force, in which case it has now reached terminal velocity because the weight force is balanced by the frictional force from the air as it's falling. So it's reached the maximum speed it can, so that's terminal velocity. If a human jumps out of a plane, you can change your terminal velocity based on how you present your body, the area that you present. So you often see skydivers kind of arch their arms and spread their arms and their legs out. And in doing so, they present a larger surface area to the air, and that creates more frictional force. And so they reach a lower terminal velocity than if they were falling feet first. So hopefully that gives you the idea for terminal velocity. Would speed be the same as velocity? Yeah, sorry about that. I tend to use the terms interchangeably and forget that you guys might have just been using speed. So yeah, at level 1, speed is the same as velocity. Could I go over the parachute part? Yeah, I probably could do with a diagram to help me do that. what I might do, we've got a couple of other things to cover, and I see that time's clicking on. So could I maybe cover the parachute part at the end? And if you want me to go over that, just hang back and I'll try and find some pictures and talk about what's going on there. Good questions, guys. Thank you. Okay, so I'm going to jump back onto work and power. So work done is energy. Work done is energy, and it's measured in joules. And so we can use the symbol. Sometimes the symbol W is used for work done, or you can use E for energy. I better put in that is the work or energy. Symbol is W or E. Power, I'll write a definition here, is the rate of transfer of energy. So that is how rapidly energy is being turned from one form into another. So light bulbs are normally a really good example because you know what a light bulb is, and you've possibly seen the rating on light bulbs. It's measured in watts, and so power is measured in watts. Oops. And so just to confuse things, that is capital W for the units there. Joules is capital J. And you could also call that joules per second. And you should be able to see that for the in the equation for power, which is power is equal to energy divided by time. Okay, so that's the energy transferred divided by time. And you might see that equation written as power equals work done divided by time. Remembering that work done and energy are interchangeable, they're the same thing. Okay, so it's just different letters to mean the same thing. So to come back to an example there, a 100 watt light bulb will transfer 100 joules of electrical energy every second. Okay. A 20 watt light bulb will transfer 20 joules of energy every second. Okay. You might have a situation where you, if you were to jump up on a table, maybe as a form of exercise, then you could work out how much energy it costs you to jump up on the table by using potential energy is equal to mgh, mass times gravitational field strength times height. And that would work out, if you know your mass and you know that g is 10 and you know the height of the table is, say, a meter, what would that be for me? Say I'm about 83 kilograms. That would be about 830 joules for me to jump up onto a 1 meter high table. If I then worked out how long it took me to do that, if I did it in half a second, then I could use my energy, which was 830 joules, divided by time, which was half a second, which would mean that my power would be somewhere in the region of 1660 watts. Okay. Realistically, it's probably not going to be that high. There's some museums and places in the world you can go to where you can get on a bicycle and you can pedal, and they've set it up so that when you pedal, you power a light bulb, provide energy to the light bulb, and it's actually really hard work to light one of the old incandescent light bulbs. Light bulbs are much more efficient nowadays, so LED light bulbs transfer more of the electrical energy into light energy, whereas old light bulbs threw out about 95% of their energy as heat rather than light, so they were actually more efficient for cooking with than they were for lighting the room. Okay, so that's a little bit about work and power. And we've got a question from an exam here about work and power. So if we had somebody riding a horse and we put a heavier jockey on, then how would that affect the work and power of the new situation, so the heavier rider on the horse? And so we've got equations that we might use here. Work equals force times distance. It's really important to note that the force in the situations where work is done has to be applied in the direction of the distance traveled. What I mean by that is that if you're pushing a desk along the ground, then you're applying a force in the direction, and so work is done. But if you were just lifting an object and then walking forwards, if you were just lifting the object, you're providing a force perhaps in an upwards direction, but you're traveling horizontally, and so no work would be done on that object. Okay, and that's sometimes quite a hard concept to get your head around. And we've been asked about power, so power equals, I'll use W this time for work done, divided by change in time. So those might be the equations we're going to use here. So if it's got the same acceleration, I might just put in larger mass there. So a heavier, larger mass rider with the same speed and acceleration would require a larger net force to maintain the same acceleration. As force, for the same, for a larger net force, they must be providing a larger forwards force. So as the force applied must be larger, the work done will be greater over the same distance. So the W value, using our equation here to support my answer, the work done value will be bigger. If they've got the same speed and acceleration, then the time must be the same as well. So since P equals work done divided by time, and time is or remains unchanged, if the work done increases, then the power must also be greater. And I think I saw the chat pop up there, so I'll just take a moment to see if there's any questions. So is power the rate at which energy is transferred, and work is how much energy is transferred? Yes, to both of those. Power is the rate at which energy is transferred, so it's energy divided by time, and work is how much energy is transferred, yeah, because work and energy are two different words that mean the same thing. Got a question, is the distance part of the work equation the final distance? It would be if you're dealing with a situation where you're pushing a desk across the floor and you push it across 5 meters of distance, then you're applying a force over 5 meters, and so it's the 5 meters that you'd be working with. So I'm not sure if I'd call that the final distance. I'd probably call it the distance traveled in the direction of the force applied. What makes up the net force? The net force is the result of all of the forces acting on the object combined. So if you've got 2 forces the same size acting in opposite directions, then this force cancels out the other force, and there is zero net force, there is no net force. If this force was slightly bigger than the force coming back in this direction, then there would be a net force, because when you overlap those arrows, there'd be a small force acting in that direction, and so we would say there was a net force in that direction. And then so work is the same essentially. Yes, work is energy. It's just another name for energy. Okay, so I'll just pop back to the share. All right, I hope that's been helpful so far. We've hit 7 o'clock. Now let me just double check what things I wanted to cover. We've got explanations relating to pressure, which we've done. Justifying the difference between energy values at the top of a slope and at the bottom. We haven't done that yet, so let's. I'll take a few moments to do that. If you can't stick around, that's absolutely cool. Thanks for turning up. We've covered free body diagrams. We've covered the link between work and power. I haven't done much in terms of calculations there, but I think you could probably give that a shot. And we've done common approaches to answering calculations and explain style questions. So for the difference between energy values at the top of a slope and at the bottom, I'm going to stop the share and I'm going to bring you up a little simulation. Where is my sim? Oh. Okay, so this is a PhET simulation, PhET, P-H-E-T, and I just, you can find this by just typing into Google PhET skate park or energy. And this is, PhET runs a whole load of simulations that are really good for helping you to understand science. So I'm going to drop into this one, and what we've got here is a skateboarder, and I think Aidan's with us. Well done on your skateboarding victory the other day, Aidan. I'm going to drop the friction down here to none, and we're going to put the skateboarder on this ramp. And what we can see is the skateboarder initially, as soon as we let them go, they're initially stationary, and then they're going to accelerate due to an unbalanced force, i.e. weight, acting downwards, and net force acting downwards. They're going to get faster and faster until they reach the bottom of the ramp, and then they're going to have some velocity, which is going to, speed, which is going to decrease as they get up towards the top of the ramp. And what's going on here is that the energy is being converted from potential energy when the skateboarder has height in a gravitational field. If we switch on the grid, we can see the height in meters here, and we can see the speed recorded here. So let's just play that. We can see the speed dropping down to 0 when the person gets to the top, and then increasing to maximum when it gets to the bottom. Okay. Now it's worth pointing out that I've turned friction off because otherwise we would expect the person to gradually slow down and get lower and lower and lower until eventually they came to rest at the bottom. And that's just because energy would be being lost from the system through friction. So as the wheels of the skateboard rubbed against the ramp, then some thermal energy would be created, and that means that there's less kinetic energy or gravitational potential energy for the skateboarder. So I've talked about energy a bit. Let's have a look over here at what's going on. So at the top of the ramp, they've got a lot of potential energy, and if I can get them right at the top of the ramp, then we've got 0 kinetic energy because their velocity is 0. They've got maximum potential energy, and then as they get faster down the ramp, we get them right at the bottom, they've got 0 potential energy, and they've got maximum kinetic energy. Because we've not got any friction, those two energy values are just going to keep on swapping. They're just going to oscillate backwards and forwards potential energy being converted into kinetic energy. If we put a little bit of friction in there, then we can see that over time we're losing some energy to heat, thermal energy, and so the person's height is gradually decreasing and their speed is gradually decreasing, and eventually all of the energy will have been lost as thermal energy, and they will have no kinetic energy left at the bottom, so they'll be stationary. Okay. I'll just pop over to chat and check if we've got any questions about that. So I saw that flagging up. Yeah, cool. No questions, just people. I think you have to go. So that's the situation with the skateboarder there. If we let that run, then eventually they would come to a complete stop. I think we're starting to see that now. Now that gives us an opportunity to look at a really a classic excellence question in the exam. And so what we might say is, if the person started at 6 meters at the top of the ramp, then what speed would they reach at the bottom of the ramp? Okay, so let's run with that. So I might just take a wee screenshot of that's right. Okay, I'll just take a little screenshot of that to remind us what we were looking at. And this is an energy question. Skateboarder started at the top of a 6 meter high ramp. What would their speed be at the bottom? Okay, now this is if you understand what you're doing with a little bit of algebra, you can make an excellence question a really quick and easy question. So I'm going to go through this, but you might want to go through it again in your own time just to make sure you understand what's going on. Any question like this is going to rely on potential energy, so I'm going to say EP being equal to EK, and we call that the law of conservation of energy. And we know that EP is equal to mgh, mass times gravitational field strength times height, and EK is equal to half mv squared. I could probably actually put the 2 in superscript there. So mgh equals half, just copy that, half mv squared. Okay, hopefully you're still with me in terms of understanding. So what we can do here is I'm going to write down next to that, maybe in a different color, some of the steps I'm taking. So what I'm going to do is I'm going to multiply both sides of that equation by 2. And the rule with equations is, as long as you do the same thing to both sides of the equation, then you're not changing any of the outcomes. Am I being seen out? What's going on there? Color, border color. Oh, text color. That's what's wrong. So I'm multiplying both sides of the equation by 2, and that gets rid of the half, but it puts a 2 on this side. So we get 2 mgh equals mv squared. So we just multiply by 2 to get rid of the fraction, the half. Okay. Now we can see m is on both sides, so we are going to divide by m, and that's going to cancel out the m's on both sides of the equation. Just copy that thing down. So I can now get rid of the m's, and that gives us 2gh equals v squared. If we want v on its own, then we need to square root both sides of the equation. And that's going to give us, I probably need to insert. There it is. So by square rooting both sides of the equation, we've got the square root of 2gh, and I'll put that in brackets just to be really clear about that. And I'll get rid of the red. And that gets rid of the squared sign on the v. So we've now got a new equation, which is square root of 2gh equals v. Now the really cool thing about that is that if we are on Earth, which we are, then maybe put a bit of space after that. On Earth, g equals 10, and so we can simplify that equation a little bit further. So the equation becomes, if g is 10, then 2 times 10 is 20, and so we get the square root of 20 times height equals v. I'm going to move this up a little bit. Okay, and so then using this equation, we can shortcut an answer. And so we know that the height was 6 meters, and so I would be using the guess method. I'm just going to, because I've got everything on the screen here and we're past time, I'm just going to I'm not going to go through the given unknown, etc. And so what we've got is the square root of 20 times 6 equals v, and so that is just the square root of 120, gives us our v value. Okay, and the square root of 120 we should have about 10.95. I think we'll just call that 11. And so the velocity would equal 11 meters per second at the bottom of the ramp. And often a question will ask you, how is the value you've calculated different in reality? Well, in reality, some of that energy that we said was conserved will have been lost due to friction, and so not all of the potential energy will be converted into kinetic energy, and so the velocity will be a little bit lower than that. Okay, right, I think that's everything I wanted to cover. I did have a question about parachutes. I'll just check to see if there's anything else in the chat before we finish up. Often when doing calculations on a graphics calculator, the symbol E can be seen. What does this mean? I think what you're probably looking at there is the times 10 to the power of. And so I probably want to give you an example of that. You can change it on your calculator so it doesn't do that, but if you're dealing with very big or very small numbers, it's often easier to use that symbol. And so what it might be is like 5, typing this in chat rather than on the slideshow. So it might be 5 times 10 to the power of 2, and on your calculator, that would, so 5 times 10 to the power of 2, which is 500, you would possibly see that as 5e and then a little raised 2 on your calculator. I probably shouldn't have thrown that raised symbol in. I was just trying to show that the 2 was superscript, you know, showing that it's an exponent. So 5e to the 2, those values all mean the same thing, and that's something called standard form or scientific notation. So you might want to Google that and just get a bit of a heads up about it if you like. But as I say, you should be able to turn that off on your calculator, but it's really useful for very big or very small values. Okay, so I'll stick around to cover a question about parachutes. You're welcome to stay. I expect it'll probably take us about 5-10 minutes. Well done for giving up your time. Thanks very much for all your awesome questions. And if you've got anything else, feel free to pop it in chat and I'll deal with what I can now. If this was useful to you, let me know and we might be able to run more in the future. Thanks guys and well done. I'll just get a parachute question ready for, oh yeah, good question. Where can we get the recording? What will I do with that? I'll probably be posting it on the teachers networks. I will also try to send a link out to you guys with the recording as well. So if I haven't done that in a couple of days time, flick me an email to remind me. Okay, so I had that question about parachutes. I'm just going to scroll back up to that question. I think it might have been asked privately. Oh no, could we go over the parachute part? Okay, so I'll go over the parachute part, but if there's a specific part of it that you want to ask me about, then please do pop it into chat so I know exactly what it is you're asking. I will do my best here. I've drawn us I've taken 2 images. So this one is with a parachute and this one's without. We're going to start off without the parachute. So the person's jumped from the plane. And we're going to have a little look at what goes on with the forces there. So let's get our weight arrow drawn up. Again, I'm drawing it from the center of the object and it's going downwards. I'll make that a little bit thicker and I'll make it, I think we used red last time for weight. So as soon as that person's jumped out of the plane, they have 0 speed the instant they jump out, but they've got weight force acting downwards. And so what's going to happen is that they're going to get faster and faster and faster downwards as they accelerate downwards. And the faster they get, the more air particles they're going to bump into every second. So as soon as they've jumped out of the plane, then they don't have any downwards speed the instant they jump out of the plane. But with every unit of time that passes, they're going to get faster and faster downwards due to that net force, the weight acting downwards. And that means they're bumping into more air particles every second. And so there's a nice little green arrow for our friction. And again, you could call it air resistance if you wanted to. I think I can get rid of that box. Okay, now a moment later, let me just tidy things up a little bit. Okay, let's call this t equals what I mean by time equals 1, it's like call it 1 second if you like after they've jumped out of the plane. Now at time equals 2, they've been accelerating for a little bit longer, and the friction arrow, the weight arrow hasn't changed, but the friction arrow has increased. Now, let's make it about that big. So the weight arrow is still bigger, and that's at time equals 2. The weight arrow is still, the weight arrow is still the same. The friction arrow is bigger, and I'll just reposition these so that the person is the same level on the page each time. I think that's about right. And then perhaps a moment, maybe at time 3, the friction has equaled, it's more than I wanted. Go. So at time equals 3, the friction force now equals, the size of the weight force. And so at that point, the forces are balanced and the person has stopped accelerating. They've reached that phrase that we used earlier was terminal velocity. Okay? So at time equals 3, the weight force and the frictional force are balanced, and we call that terminal velocity. The fastest speed that object can travel at as it falls through the atmosphere. Okay. I think off the top of my head for humans it might be about 54 meters per second. I'd probably need to double check that, so apologies if I've got that wrong. And again, it depends on orientation, so how the person presents themselves to the air, whether they're spread out or whether they're, tucked into a ball or, going feet first. All right, so what happens next then is that the person opens, sometime later, the person opens a parachute. If you've never been skydiving, I can heartily recommend it. Great experience. And generally, you want to be in the air for as, you want to be enjoying the experience for a long time. So you might enjoy terminal velocity for a while until you open your parachute. So here's our new situation, time 4, with the parachute opened. Now, as soon as the person opens their parachute, then we've got a big, much bigger surface area, and so we're bumping into more air particles every second. I feel like I should probably start this on a new page, actually. Let's start it here. The weight force is the same, because even though you've popped the parachute, it was still on you when you were falling anyway. And so your weight force hasn't changed because there's still the same amount of you, there's still the same mass of you, you're still in Earth's gravitational field, so your weight force hasn't changed. But what has changed is that now you've got this huge frictional force. And that means that the net force is now acting upwards. And because the net force is acting upwards, in situation time 1 and time 2, the net force was downwards, so the person was accelerating downwards. In time 3, the forces were balanced, so there was no acceleration, so the person had reached constant velocity, and we called that terminal velocity. In time 4, when the person's opened their parachute, we've now got this massive frictional force, and so the net force is upwards. Sorry, I wanted to copy that. So the net force is now upwards, and that means that the acceleration is upwards. The acceleration is upwards. Now, the person still has a speed downwards, but what the upwards acceleration means is that they're now slowing down. And generally, when you're falling through the air, you want to slow down before you hit the ground. And so the parachute lets us do that. It lets us reduce our falling velocity until it's at a safe level for hitting the ground so that we don't get injured. So the net force is now upwards. The acceleration is upwards, even though the person still has speed downwards. And then because they're accelerating in the upwards direction, that means that their speed downwards gets smaller and smaller and smaller until they reach a new terminal velocity. As they get slower and slower and slower, that frictional force will decrease because they're slowing down. They're not hitting as many air particles every second. And so the frictional force decreases until it is equal to the weight force, and then a new constant speed or terminal velocity has been reached. Okay, wow, lot to take in there. So I might just try and do a situation at time 5 just to show what I was talking about there. But to do that, I might just have to move some things over a bit. And while I'm doing that, if you've got any questions, I'd love it if you could fire them into chat. Oops. I think that's going to get a bit cramped, so I might just actually copy that time 4 diagram onto another page. And then I'm going to make this so time 5. And so at this stage, the person's speed has decreased enough so that their friction arrow has decreased to the same magnitude as the weight force. Yeah, they look about the same size. And so that a new constant speed has been reached. I might say a new lower constant speed has been reached. Okay. Now that's far more detail than you would probably need to give in an answer, but hopefully that helps you understand what's going on there. Yeah. Okay, I'll just check chat. When it's accelerating upwards, would you be able to say it's decelerating downwards? Yeah, I'd probably say I might say that they have a speed downwards and are decelerating, meaning that their downward speed is getting slower. So yeah, you could say that. Just be careful, you know, that you're conveying exactly what you mean in the wording that you used. Good question, Jessica. Yep, so I've had a question about the distance in the work equation once again. I'll just give it a moment to see if anybody wants to ask any more questions about the parachute situation, and then I'll do that. Okay, so I'll go over the distance in a work equation once again. Just trying to think how the best way to do that is. Oh, let's use we could probably use another PhET simulation. Okay, so if you we've got a person here and an object on a skateboard, and they apply a force to that skateboard, and we could see there that the applied force was, say, about 100 newtons, and and we know what distance they've covered, then we can work out the work done. So they're applying a force of 100 newtons. Let's say that they are doing that over a distance of 150 meters. So what we'd be looking at there is work done is equal to force times distance. So I said that the force applied was 100 newtons. The distance was 150 meters. Our equation is work done equals force times distance. And so that would be 100 times 150, which would be, what have we got there, 15,000 joules of energy. So the work done would be 15,000 joules. Does that answer your question? Yeah, okay, the ramp situation. Okay, so, yeah, great question. Like in a ramp, how do we want to deal with that? What I would do with a ramp question is I would, where's my resume share? Okay. What speed would the mass have after 160 meters? Do you mean 150 after the 150 meters? Okay, so I'll just jump back and answer that quickly, and then I'll go on to the ramp one. So what I would do in that situation, so the speed after 150 meters, assuming it was stationary to start with, I would say that we've applied 15,000 joules of energy, and we could say that EK equals half mv squared. And so we can use that equation to work out the velocity. And so we'd rearrange that, and it becomes V equals 2ek, square root of 2ek over m. So I'm just going to insert the right symbol here. So V equals square root of 2ek, and I'm not going through the rearrangement here just for speed in terms of time rather than, that's a bit confusing. So V equals the square root of 2ek over m, and so it will be the square root of 30,000 joules divided by mass. I can't remember what mass the object was. So let's say that it was 20 kilogram mass after 150 meters. And then that would just be 30,000, square root of 30,000 divided by, what did I say, 20? I could probably have done that in my head. And then square root that gives us, I've got 38.7 meters per second. 38.7 meters per second. Okay. So hopefully you can follow what I've done there and do those steps for yourself and just verify that. And it's a great thing to do, to give yourself sample values, see if you can work them out. I'm not sure. Yeah, I think actually you could record the speed. I don't know if it actually gives you a value. Oh yeah, there we go. And so you could you could run that. I don't know if it gives us distance on this, but you could have a play around with that and check your calculations to make sure you follow what's going on. Okay. So the work done with the ramp, which is a really awesome question. Okay, so if that's our ramp and we've got an object going up it, so the question might be how much work is done in moving the object from here up to the top of the ramp. And so I would be looking at drawing a line here and then recording the height from the midpoint here to where it would be at some time later. So I wonder if I can. Oops. So the change in height is what's important here. We'll make that blue, shall we? I'm actually going to call that change in height. It's a bit more specific. So that blue line represents the change in height. And so it doesn't really matter how much force you're pushing up the ramp with, assuming that all of the energy you're putting into the object is converted into gravitational potential energy as it goes further up the ramp. Then if you know that change in height, then the work done can be calculated using EP equals mgh. And that's what I would suggest in this situation, is I would use EP equals mgh, assuming you know the mass of the object. What do we want the mass of the object to be? Let's call it 10 kilograms. It's a nice easy number to work with. And the change in height is, what should we say, 2 meters. Then we would be looking at EP is equal to 10 kilograms times 10 for g, the acceleration due to gravity, times 2. And so the EP in that situation would be 200 joules. And that is the work done. Okay. And so I guess what you need to do is look at the situation with the ramp and recognize that it's the change in height that's important, and that is what determines how much work is done. So, effectively we're ignoring that horizontal dimension and just focusing on the vertical dimension in those situations. I think that perhaps answers your question, but if you'd like to ask me to clarify, I'm happy to. Yep, good question. How is the work the same when the distance of the ramp is longer? It doesn't matter how long the ramp is. The only thing that's important there is the change in height. So if we had another situation where the ramp was, really steep, I guess you could make the ramp steeper and steeper and steeper until you get it vertical, at which point you're just lifting the object straight up. And so all the ramp does is make it easier for you to apply the same energy over a longer distance. But the amount of work done, regardless of whether that's done straight up or whether it's done up a ramp, is the same. Because you're applying a force to oppose the weight of the object. So you're having to provide a force if you're lifting it straight up. You're just providing that force directly against its weight. If you're doing it up a ramp, then you're applying the force against its weight in like an increment, if you like, a smaller version of its total weight, which means it's easier for you to do because you're spreading out that amount of energy over a longer distance. My pleasure. Okay, I'll stick around for a moment in case there's any other questions. But yeah, thank you guys very much for your involvement, and I hope that's been helpful to you.